Welcome back. So, in today's video lecture, uh, we will start module 3. So, we'll from now onwards, we'll look at the module 3. So, mainly in module 3, we will cover several aspects about the surfactants and micelles. Okay, we will talk about what is surfactant and what is micelles. Okay, and we will also cover some of the important topics like what is known as critical micellar concentration, what is packing factor. Okay, why micelles assume a certain shape, right? We look at what is the change in Gibbs free energy of micellization at standard reference state. We will look at what is the HLB guidelines. Okay, one has to follow if you want to, uh, you know, uh, use the surfactants for various applications like detergent application, emulsion application, right? Right, and then we will look at uh, absorption isotherm, right? Gibbs absorption isotherm. So we have got so many topics to be covered under the module 3. And in today's video lecture, we are going to look at the overview of surfactant and micelles. Right? Let's begin. Yeah. Yeah. So we will start from the uh, overview of surfactants and micelles. So micelles are also micelles meaning they are aggregate of surfactants, right? Okay, aggregate of surfactant and monomers, you can say. When I say monomer, let's say individual surfactant, right? So it is basically nothing but aggregation of surfactant molecules, right? So sometime, often, people also regard micelles as association colloids. Okay, because why this is also referred to as colloid, because the size of the micelle usually range up to a few hundred nanometer, right? And because of that characteristics, people also call micelles as association colloids. Okay, uh, micelles can also be treated as colloids, right? Right. So we will look at in today's lecture, what are different types of surfactants and the applications, right? We'll also try to cover some of the naturally occurring surfactants, right? Okay, so before we begin, we'll also see what is the application of micelles. Micelles are used in many applications. If you want me to list few, maybe you can say that it is also used in wastewater treatment. Okay, or you can also say enhanced oil recovery, right? All right. Yeah. So now we will look at the the surfactant itself, right? First, so surfactant usually an amphiphilic compound. It has got two parts. Okay, one is the head group. Okay, yeah, which is basically hydrophilic in nature, and you have a tail group. This is usually constituted by hydrocarbons. Okay, so we also call this tail group as backbone of surfactant, and usually this tail group, is hydrophobic in nature, right? All right. So there are different types of surfactants. You would encounter, a surfactant with two tail group, or a surfactant with two head group, uh, right? Like deuterionic surfactant, okay, or Gemini surfactant. So there are different types of surfactant depending on the application. One would have to look at and explore, right? Right. So let's talk about different types of surfactants, okay? Okay, when we talk about different types of surfactants, let's let's have a broad classification, right? So we can say that anionic surfactants. So the first one to uh, you know to be included in the list is anionic surfactant. You can give an example. Let's say SDS, right? Usually the CMC for SDS is 8.2 millimolar, okay, right? And SDS is sodium dodecyl sulfate, okay. And the next one is cationic surfactant, okay. One good example which people often use is CTAB, okay. This is nothing but cetyl tri methyl ammonium bromide, okay, which is basically a quaternary ammonium salt. It has good antiseptic properties, so you would find this in a medical application mainly. The CMC of this is usually 1 millimolar, okay, right. And the last but not least is non-ionic, okay. This one doesn't belong to cationic or anionic, okay. There are some commercially available non-ionic surfactants. If I can name few, I can say what is known as tween, okay, or span. So tween is usually polysorbate based, right? Polysorbate based non-ionic surfactant. And span is usually sorbiton, right? Usually sorbiton based non-ionic surfactant, okay. So we can list few applications of the surfactant. You would find in many application in many industries, okay. Let's say pharma industries, right? Or you can say healthcare, or you can say mainly in cosmetics also, right? So these are so one can list several applications, but these are mostly, I mean, widely used, right? Surfactants are widely used in these industries, right? Okay. So now we can look at some of the naturally occurring surfactants, okay. These are not made synthetically, right? These are available by nature, right? I mean, these surfactants exist in nature, right? Say for example, I can give a good example of phospholipids, right? This is usually the lipid based surfactant. It contains two tails usually, right? All right. So the next one is what is known as DPPC. Okay. So this is usually again phospholipid based only family, phospholipid family. This is also regarded as people I mean, sometime, call it as like, pulmonary, right? Pulmonary surfactant, okay? Because this is the main constituent of pulmonary tract, right? And it is also called as the lung surfactant, okay? Why? Because this DPPC type surfactant, which is basically a main constituent of the pulmonary tract, so this is naturally formed, right? So what happens is this helps in reducing the surface tension at the liquid gas interface, right, in the pulmonary tract. So which means that it reduces the work of breathing and makes the breathing a lot easier, right? So there are several naturally occurring surfactants. One can give several examples, but I just want to list few in the interest of time, right? So now what we will do is we will look at the phase diagram of surfactant, okay, and we will look at the packing factor, packing consideration, right? Why a micelle has to assume a specific shape, right? And those aspects we will see now, okay?
Yeah.
So now let's look at the phase diagram of surfactant, right? Dilute surfactant water system. So you can see in this phase diagram there are three different states, right? One is the monomer state, micelle state, hydrated crystal state, okay? And apart from this, you would also need to know what is known as Kraft point, cloud point, which we will cover now. So what is very important is the operating line, which you will be operating, right? For example, if you want to, synthesize micelles, you should also know you should control, you should modulate not only the concentration but also the temperature, because even though you above the CMC line you can make micelles, what is so important is you should be always away above the Kraft point, right? If you are above the Kraft point and above the CMC line, only then the micelles are favorable, right? So if you are going from monomer to micelles, you should know that two parameters, right? One is the Kraft point and as well and the other one is the CMC, right? So if you are above the CMC and if you are not above the Kraft point, micelle state you cannot attain, okay? On the other hand, you may be above the CMC line, but you are below the Kraft point, so one would achieve the hydrated crystals, right? So in this state, what will happen is the surfactant will precipitate out in the form of hydrated crystals, right? So one should avoid this point if you are keen on making the micelles, right? So monomer state, even though you are above the Kraft point, but if you are below the CMC line, you would surely get the monomer state. So you cannot achieve this conversion from monomer to micelle state. So this phase diagram is very well important. So that you know what are the operating parameters, right? Temperature and concentration. One has to fix the temperature and concentration. If you are if you are interested in making one of these achieving one of these state, right? So there is something called Kraft point. As you know, just now we described, Kraft point is the minimum temperature at which a surfactant can form micelles, right? So above which the surfactant can form micelles. At the same time, the cloud point is the extreme limit, right? The maximum point. Even though you are above the Kraft point, if you are above the cloud point, what will happen is the surfactant, the micelles will precipitate out from the solution, right? So, I mean, it will make the sample turbid. The solution will turn into cloudy or turbid. Okay, one has to avoid this situation by knowing the cloud point of the sample, right? Yeah. So now we'll look at the packing consideration and the shape of micelles. As you know, formation of micelle itself is nothing but a self-assembly of or self-organization of the surfactant, right? Molecules, right? So surfactant can assume a different shape, different equilibrium shape, okay, right from spherical to cylinder, okay, and lamellar and several of them. But what decides them to assume a particular shape is the question that we are asking, okay. There is something called a packing guideline or packing factor. It is just a guideline, but it tells us that, let's say, if you have got some particular packing factor, what one can understand is that this micelle will only assume a particular shape which corresponds to this particular packing factor. Okay. For example, if your packing factor is, let's say, less than 1 by 3 or equal to 1 by 3, you can say that this micelle will only assume a spherical shape. Or if it is, let's say, so you can, the similar way, you can also do this exercise to know if you, let's say, if you want to know whether apart from the spherical shape, if it forms a cylindrical shape, for that also you can use this guideline, right? Whether it will assume spherical shape or cylindrical shape. Now, what decides, what dictates the surfactant to assume a certain shape is because the that comes from the fundamental nature of the surfactant or fundamental shape or structure that they assume, right, at the individual surfactant level itself. For example, you can say that this surfactant, themselves, assume into or put them into a cone-like shape, right? In this zigzag, when they accept this zigzag path line, right? When they accept this zigzag path orientation, they will assume a cone-like shape. You know that when you pack this cone, right, in a compact way, one would get the spherical shape, right? So the question that we are asking is, what decides this shape is a couple of parameters. I mean, a few parameters that decide. One is the head group, optimal head group area. Okay, let's say if optimal head group area becomes larger and larger, one would walk towards this direction. That means you will go from cylinder to truncated cone to cone. Whereas if head group area becomes smaller and smaller, one would walk in the opposite direction, which means that you will get inverse truncated cone or inverse cone, right? In this zone, if you're moving, you will most likely stabilize oil in water emulsion. In this zone, if you are moving, you will most likely stabilize water in oil emulsion. Okay. So similar is the case with the other operating parameters like the volume of the tail and critical chain length, and volume of the tail and critical chain length, right? Right. So what decides the surfactant to choose the optimal head group area? That is based on the minimal energy configuration. For example, this head group of surfactant usually contains some functional groups, like let's say carboxylic acid group, amino group, right? So this head group, when they come very close to each other, there will be a repulsion, right? Whereas the tail group that contributes to the hydrophobic interaction, and when tail group comes closer, there will be hydrophobic attraction. There will be attraction between the two. So there has to be a right balance between the repulsive force and attractive force. At some point, when attractive force and repulsive force meet each other, right, there will be a minimum energy. The system will attain a minimum energy, and that happens exactly at this point. That is nothing but the optimal head group area. Okay, so at this optimal head group area, at minimum energy configuration, it will assume a certain fundamental structure or shape, and that's how they will assume if they assume a cone like shape fundamentally, then they will assume spherical shape when it forms micelles. Okay, when it assumes truncated cone like shape, then they will assume most likely, or when they assume cylindrical shape fundamentally, then they will assume cylindrical micelles. So in this way, one would get micelles with a different shape. Okay, and if you want to get more insight into these topics, one can refer to the book authored by Israelishvili, right, on intermolecular and surface forces. Right, now we can see how this packing parameter can be calculated. So it's basically a number balance, right? So what one can do is, you have on the left hand side the volume of the surfactant, right? Here R refers to the radius of the micelle, which is measured up to the apex of the cone. So it goes from one end, that is tip of the cone, to the apex of the cone, and this one is measured up to the volume which is considered up to the apex of the cone, right? From the tip of the cone up to the apex of the cone. So if you the ratio of these two should give the number. This comes from the volume basis. Whereas the similar way, if I do surface area basis, like the radius of the here, the radius constitutes the head group constitutes the surface area, and when you divide the surface area with the area of the head group, one would get the number. But these two numbers has to balance each other. So in this way, you would get this ratio, right? But what we want to do is, we want to forcibly introduce this parameter that is called chain length, so that this becomes a dimensionless quantity. So in this way, if you on the both the side, if you introduce this chain length, one would get this packing factor, right? And you see this packing factor has to be less than or equal to 1/3, okay? Because here the radius is measured from the tip of the cone till the apex of the cone, whereas the chain length, critical chain length, since they assume zigzag path, and at the liquid core, right, they will assume extended conformation, right? So in any case, this LCT, critical chain length, will be either greater than, always greater than or equal to the radius of the micelles, right? Depending on the configuration of the surfactant. So in this way, one can say surely that the packing factor will always be less than or equal to 1/3. So similar exercise, you can do it yourself, to know what is the packing factor for cylindrical micelles, right? You can check that this is 1/2, right? Now, there is something called Tanford equation, which is again kind of empirical equation, which is based on the number of carbon atoms present in the chain. So this you can use some time to understand what is the volume of the tail, right, and what is the critical chain length, right? If these data are not given, one can use this Tanford equation to calculate these parameters as well. Now, what I have shown here is the micelles with different shape, and all corresponds to packing factor, right? Different packing factor. You can verify yourself for these micelles. For these micelles with a different shape, right? Okay. So we will stop here. We will continue from the next lecture. Thank you.